There are a few types of objects which are given special names within a category. The first one is known as an initial object. So an object I in a category C is initial if for all objects in C, the home set from I to any object A contains only a single element. So what that looks like is that you have your object I, and for any object A, including I, there is a single morphism from I to that object. And of course, because we must always have the identity morphism on I, the only morphism in the home set from I to I is the identity morphism if I is initial. The next type of object is a terminal object. An object is called terminal in C if for any object in C, the home set from the object A to our terminal object T contains a single element. And so what that means is basically the opposite of the first case, that for any object A in the category, we have a single morphism coming into our terminal object T, including, of course, T itself, which also in this case will only have the identity morphism as constituent in the home set from T to T. Finally, a zero object is one which is both initial and terminal in the category. We'll conclude by proving two quick things about initial and terminal objects, namely that they're isomorphic. We'll start with initial objects. So the theorem is that any two initial objects of a category are isomorphic. Suppose A and B both initial in C. Then the home set in C from A to B has a single object. Call it F from A to B. And the home set in C from B to A also has a single morphism. Call it G from B to A. Now, because the domains and codomains line up of these two morphisms, we can compose them to get G after F, which takes us from B to A, and then from A back to B, as well as F after G, which takes us from A to B, and then from B back to A. But of course, we already have morphisms going from B to B and from A to A respectively. That is, the identity morphisms on A and B respectively. But again, of course, A and B are both initial objects, which means we can only have one morphism going from B to B and from A to A. That is, 1B must be equal to G after F, and 1A must be equal to F after G. But then this exactly satisfies the definition of an isomorphism, which means that A and B are isomorphic, which is what we were trying to prove. Finally, an almost identical argument shows us that terminal objects in a category are also isomorphic. And of course, this is because in the same way, the home set from A to B for two terminal objects A and B will correspond to just a single morphism from A to B. And the same from B to A, call it G. And from here, the exact same argument applies, showing that any two terminal objects are isomorphic.